Good morning, good afternoon, students. We'll now move on to our 10th lecture under this module. Another two more important concepts are there under this, that is instance-based learning and reinforcement learning. Okay, so under instance-based learning, how is it different from the algorithms that we have learned so far? And after that, reinforcement learning will go through. Yeah, in the last class, we completed hypothesis testing concept by two topics, paired t-tests and practical considerations to perform this kind of tests. In today's class, we are going to cover on instance-based learning and k-nearest neighbor learning. What is instance-based learning? How is it different from the algorithms we have learned so far? So far, we have seen algorithms like decision tree algorithm, neural networks, multi-layer perceptron algorithm, and gradient descent algorithm, and candidate elimination algorithm, and finders algorithm. Lots of algorithms we have covered, right, so far. But how they are different from instance-based learning? In the algorithms we have seen so far, we try to make the machine learn from the training examples altogether and formulate a target function, say f, right? But in instance-based learning, all the methods simply store the training examples. They don't try to learn from the training examples as and when they encounter each of the training examples. Say in candidate elimination algorithm or finders algorithm or decision tree algorithm, whenever some training example is encountered, immediately something will be learned by the machine learning model. But in instance-based learning, the machine first stores all the training examples and keeps its task to the last phase, keeps its task to the later phase. So instance-based learning methods simply store the training examples at the first. It doesn't start learning as and when it encounters the training examples. It just stores all the training examples first. Now, generalizing beyond these examples is postponed until a new instance must be classified. Now, normally other algorithms will generalize based on whatever training example they encounter. They learn some extra, additional, some concept. Now, second training example is encountered. Say they now learn some more additional concept. Now they encounter third learning example. They learn some additional target concept, right? They try to refine their target concept as and when they encounter the training examples. But that kind of generalization is kept pending to the last phase in this instance-based learning. Generalizing beyond these examples is completely postponed until the new instance must be classified. So it just stores the training examples. Now when some new data point is given, it will try to compare that data point with all the training examples and tries to classify that new data point as to belonging to one class or the other class. Say there are some data points like this, star points and circle points, right? Now a new data point, now whenever the machine learning model is given these training examples, it just stores the values. Now a new data point, say plus, is given to the machine learning model. At this phase, that is at the last phase, after storing all the training examples, the model compares this plus data point, that is the new data point, with stars and with circles. Now, this new data points features, whether they are matching with these data points features, with this class's features or this class's features, it will try to analyze. And based on some calculations, it will either assign that new data point to star class or the circle class. Okay, so how is the classification postponed? How is some decision or how is some task postponed? It is postponed till the end, when a new data point, till a new data point is given. Generalizing beyond these examples, training examples, is postponed until a new instance must be classified. Now a new instance plus symbol is given here, and once it is given, then it will start comparing its features with already existing training examples features. Now if this plus features are almost similar to this star features, then it will assign it to this class, or if it is almost similar to circle features, then it will assign it to this class, circle class. Okay, so what did you observe here? Only when the new training example is given, the actual task of categorization, learning from the features of the new data point, whether it is matching to a particular class and categorizing it, that will take place only at the ending, not at the beginning. But in eager learning algorithms, what we do, this kind of instance-based learning algorithms are called as lazy algorithms. Why? Because the learning is postponed till the end. But in eager learning algorithms, where we discussed about decision tree, candidate elimination, find-S algorithms, multi-layer perceptron algorithms, there what happens, as and when the training example is encountered, it will refine its hypothesis based on the combination of attributes that it comes across, right? Say first training example, some combination of attributes, it learns something from that training example. Yes, that is H. Now this H is refined, more generalized. Initially it will be more specific. You remember in candidate elimination algorithm, more specific hypothesis, more general hypothesis, right? In that way, the hypothesis initially will be more specific. Now, as and when it encounters each and every training example, the hypothesis will be refined to more generalized stage. But that kind of continuous learning doesn't happen in instance-based learning. In instance-based learning, all the training examples are initially stored, and generalizing beyond these examples is kept postponed till the end, where till a new instance is given to be classified. Now, because the new instance is given, the new instances features are compared with the existing data points, and with which existing data points it is matching, it will be assigned to that particular class. How that exact classification is done, I'll explain you later, but preliminarily you just keep this in mind. Its features are compared with the existing training examples and classified accordingly. Okay. Now, instance-based methods are sometimes referred to as lazy learning methods because they delay processing until a new instance must be classified. They doesn't start any processing at the storage phase. In the initial phase, it just stores all the training examples. Then in the later phase, when a new data instance is given to be classified, then it will wake up, then starts comparing its features with the existing training examples features and classify it accordingly. That is why, because the processing is kept pending to the last stage, they are called as lazy learning algorithms. Whereas the algorithms we have learned so far till fourth module, we can generally call them as eager learning algorithms. Okay. Now, a key advantage of this kind of delayed lazy learning, the key advantage of this learning algorithms, lazy learning algorithms, is that instead of estimating the target function once for the entire instance space, in candidate elimination algorithm and find-S algorithm and decision tree algorithm, the hypothesis is learned over the entire instance space, over the entire training examples. That hypothesis will be in accordance with all the training examples given. It will be consistent with all the training examples given, right? The hypothesis which is in consistency with the training examples given, then we say that is the best hypothesis, right? Now, but that hypothesis is learned over the entire instance space. But in instance-based learning, These methods can estimate it locally and differently for each new instance that has to be classified. Now, whenever a new data point is given, that new data point is compared with each of the training examples. Now, with which example it is most similar, which class that example belongs, even this also belongs to that particular class. The new data point also belongs to that particular class to which its similar training example belongs to. Okay, that is why it is called as instance-based learning. Until a new instance is given, the classification is kept pending. Okay, so is the name instance-based learning. Now read this, it will be more clear. A key advantage of this kind of delayed, it is delayed till the last phase, lazy, because it doesn't start processing until new instance is given. Learning is that, a key advantage of this kind of learning is that instead of estimating the target function once for the entire instance space, like learning a hypothesis for all the training examples, which is consistent with all the training examples. What we are doing here, these methods can estimate it locally and differently for each new instance to be classified. A new instance is taken, compared with all the training examples, only then classification task is performed. Until then, it just stores the training examples. It doesn't perform any other kind of processing until the new example is given, until the new data point is given, or until the new instance is given. Now, instance-based learning methods such as nearest neighbor and locally weighted regression are conceptually straightforward approaches. There is nothing complex underlying that. It is very straightforward. You can easily understand. These are the main algorithms: nearest neighbor, k nearest neighbor algorithm for discrete value target function. Means if you want to perform a classification like yes or no, a transaction is fraudulent or not, a customer is loyal or not. In such kinds of cases, you use k nearest neighbor. But if the end label is some continuous value, say you want to predict the sale price of a house, or you want to predict the stock price of a share, or you want to predict the climatic condition, the weather, temperature on a particular day. All these are continuous value target functions, right? For that we use locally weighted regression. But all these approaches under instance-based learning are straightforward. There is nothing underlying complexity in that. Now, learning in these algorithms consists of simply storing the presented training data. It just stores the presented training data. Only when the new instance is given, it will be awakened. It will start processing by comparing that new instance with the existing training examples. Right? Same as you didn't join the class unless I have sent a message. Because you are lazy learners. Okay, learning in these algorithms consist of simply storing the presented training data, and when a new query instance is encountered, a set of similar related instances is retrieved from memory and used to classify the new query instance. What is happening? When a new query instance is encountered, when this instance-based learning model is given a new instance, it will start comparing that new instance with the training examples with which it is matching the most. Those examples will be retrieved from the memory, and out of these 4 examples, say it is matching more with 3 of them and matching less with 1 of them. In that case, this training example will be put into this particular category. Why? Because it is matching with most of these examples, but only 1 of this example. Means most of the data points in a particular class and only 1 data point in another class. So obviously, based on majority vote, it will belong to this class, not this class, right? That is how the classification is done. Now, one disadvantage of instance-based approaches is that the cost of classifying new instances can be high. Why? Can you just think about it? Why it is considered as a disadvantage? Instance-based approaches, disadvantage is that cost of classifying new instances can be high. Why? Because none of the processing is done at the beginning. Only when a new instance is given, it will be compared with all the training examples, and only then it will be classified into a particular training examples class. For this, lot of comparison is required, and learning from the features of this new instance to compare with the existing instances, that computational cost will be too high, because every computation, every processing part is kept till the end, pending. It is kept pending till the end. Okay, that is why the computation will be very high. And second disadvantage to many instance based approaches, especially when we consider nearest neighbor approaches, is that they typically consider all attributes of the instances when attempting to retrieve similar training examples from memory. So whenever you are given a new data point, this will be compared with all the attributes of the existing training examples. Now consider, in a data set, only some attributes are playing very important role in the classification task, and other attributes are not that important. In such cases, when we take this nearest neighbor approach, in this approach, all the attributes values are compared with the new instances attributes. Not only the significant attributes, but also the unimportant attributes also will be considered to compare with the new instance. What will happen in this case? In this case, because of comparing all the attributes, sometimes even similar kind of points may not fall into one particular class. Did you understand? This explanation is little confusing. You have to focus. I'm trying to tell, when a data set is given to you, in that, say if you have 10 attributes, in that only 8 attributes play significant role in deciding the outcome label, target label, and 2 attributes are not that significant in determining the outcome label. Now, in k-nearest neighbor, what it does is, it doesn't take only those 8 important attributes. It takes all the 10 attributes into consideration in order to match that new instance with the existing instances. So that will sometimes may deviate the categorization. Sometimes, though it has to fall into a particular category, because of this unimportant variables being given equal importance along with the important variables, it may be categorized into a wrong class. That is another disadvantage. Okay. Now, the most basic instance-based method is the k-nearest neighbor algorithm, as we have learned in the beginning. Now, this algorithm assumes that all instances correspond to points in the n-dimensional space R power n. Why we are calling it as n-dimensional space? Sometimes we can take a space like this, 2-dimensional space, where you have various data points. Right? Here we are taking it as 2-dimensional space. Sometimes we may project it upwards so that it becomes a 3-dimensional space. So overall, this algorithm assumes all the instances means data points. All the data points correspond to points in the n-dimensional space R power n. Okay, in this case, we are taking a 2-dimensional space. But if you take length, breadth, and width also, then you can, length, breadth, and height also, in that case, we can call it as 3-dimensional space. Now, if you have multiple such spaces, you can call it as n-dimensional space, right? But for simplicity, for making you understand, I'm just treating it as 2-dimensional space with x-axis and y-axis. And all the points are lying in this 2-dimensional space. Now, the nearest neighbor of an instance are defined in terms of the standard Euclidean distance. What is this Euclidean distance? You remember in your PUC you might have studied. In order to calculate the distance between a point x1, y1 and a point x2, y2. What is the formula for Euclidean distance? Square root of x1 minus x2 whole square plus y1 minus y2 whole square. That will give you the Euclidean distance, right? Same thing we are applying here also in k nearest neighbor. There are other distances like Mahal-Nobis distance and some other distance measures, but most generally used distance measure in k nearest neighbor is Euclidean distance. Now in this case, in this particular problem, how the instances are compared. Say when a new instance is given, this circle point, this features, say it has attributes A1, A2, A3, and all these data points also have 3 attributes. Now the distance between attribute A1 of new instance and attribute A1 of this instance is calculated. Again, the distance between attribute of A2 of new instance and attribute A2 of this instance will be, existing instance will be calculated. In the same way, distance between every attribute of the new instance and the every attribute of existing instance is calculated and summed up. And this is repeated for every other existing instance. Now, with which instance it is nearer? The distance between the new instance and which other instance is lesser, that new instance will be assigned to that particular class. Okay, say the distance between this circle new instance and this point is less. So this will be assigned to a class which belongs to circle class. Which belongs to this particular existing instance. This new instance will be assigned to this class to which the existing instance belongs to, with which the distance is lesser, between which the distance is lesser. We found that this existing point and this new instance, distance between them is lesser. So it is assigned to a class to which this particular instance belongs to. Okay, this is how k nearest neighbor is executed, right? So the nearest neighbors of an instance are defined in terms of the standard Euclidean distance. For this, for calculating the distance, they are using this Euclidean distance measure. Now, more precisely, let us understand it more clearly. Okay, I have just given you an overview so that when we are going with the mathematical terms, you will easily understand. More precisely, let an arbitrary instance x, arbitrary instance means this is the new data point x, be described by the feature vector a1 of x, a2 of x, and so on up to n of x. Means it contains n attributes. It contains here n attributes. First attribute is denoted by a1, second attribute is denoted by a2, and so on, right? Where ar of x denotes the value of the rth attribute of instance x. We understood this. Then the distance between two instances x1 and xj is defined to be d of x1 and xj. How do you denote that? Distance between xi and xj, points xi and xj, d of xi and xj. Now how do you define this distance? According to Euclidean distance. Now how do you mathematically represent this? D of xi comma xj is equivalent to, you already know the formula, right? Square root of x1 minus x2 whole square plus y1 minus y2 whole square. This is the formula for Euclidean distance, right? Simple maths which you have learned in your PUC. Now, same thing is mathematically represented here. Listen carefully. Now, you are representing it generally for the rth attribute, right? For every attribute, the distance is calculated. So that you are taking generally as r from 1 to n. How you are denoting that? The difference between attributes of the new instance and the existing instance. It is AR of xi, the new instance, minus AR of xj, the existing instance's attribute. Find the difference between them, square it, add them up, and find out the square root. That will give you the Euclidean distance between two instances xi and xj. Okay, see in this plane, you have some points like this. Now you are given a new data point. Now this has attributes A1, A2, A3, and this also has attributes A1, A2, A3. Now the distance between A1 of new instance and A1 of existing instance. Find out the difference, square it, plus the second attribute's difference between both the instances, square it, plus difference between the attributes difference between the instances third attribute, square it, add it. Now over this summed up value, apply the square root. That will give you the distance measure, Euclidean distance measure between this point and this point. In the same way, distance between this point and this point is calculated. This point and this point is calculated. This point and this point is calculated. Finally, wherever the distance is lesser, that is the instance it is matching with. Got it? This is how the Euclidean distance is measured. The similarity of the instances is calculated. Now in instance neighbor learning, the target function may be either discrete valued, in nearest neighbor learning, the target function may be either discrete valued or real valued. Sometimes you may have multiple classes into which the new instance have to be classified. Sometimes you may have a target function as continuous valued variable, continuous valued function that has to be learned. Okay, now let us first consider it as discrete value target function. Let us first consider learning discrete value target functions of the form. How do you represent it? The function f, which is defined as from the n-dimensional plane, you're mapping it to a class, set of classes. It may be binary classification. In that case, we will have only two classes. In case of multiple classification, we will have three or more classes. Right? So where V is the finite set V1, V2 and so on up to Vs. If it is binary classification, you will have only V1 and V2. But if it is multiple classification, you may have V1, V2, V3 classes and so on. Okay, lots of classes. The new instance must have to be classified into the appropriate class. Okay. Now the k nearest neighbor algorithm for approximating a discrete value target function is given in the table. Simple algorithm. Let us see the steps. Because you already have the basic idea, you will easily understand this algorithm. What is the training algorithm? What does the training algorithm take here? For each training example, already the training examples are saved. Okay, and you know that in instance-based learning that already all the training examples are saved. Okay, that have to be written as a step. For each training example, x is the set of all the attributes, and f of x, that is the target label. For each of such formatted training example, add the example to the list of training examples. Keep adding, keep storing all the training examples. The data set is given. Now how do you, how a k-nearest neighbor algorithm can be applied on the data set? First, all the data points in the data set are stored into the memory. All the training examples in the data set are stored into the memory. Now, when the new instance is given to be classified, only then the actual processing starts. Now, given a query instance xq, consider this as your new instance. Query instance xq to be classified. The new instance is named as, is taken as xq, which has to be classified. Now, let x1, x2 and so on up to xk denote the k instances from training examples that are nearest to x cube. Now, let us take some training examples in the data set which are nearest to this new instance x cube. This is the new instance, right? New instance x cube. Now we are taking k instances, x1, x2 and so on up to k. Means k training examples which are nearest to this new instance. Let us take them. Now return. What has to be returned now? The distance of each of those training examples with this new instance. The distance between the new instance and all those training examples which are nearest to x cube, that has to be returned. Only then you can find out which training instance is very near to this new instance, right? For that, what is the formula we are giving here? Argmax v belongs to v. What is v? The number of classes we want to classify into. Binary classification means you have two classes. Multi-classification means you have multiple classes. So how does this v belong to v actually play an important role here? Let us see. First, let us see what actually is added up. Then we'll see what we are trying to maximize, right? We are trying to add delta v comma f of xi, where delta a be equal to 1 if a is equal to b. Means if the new instance is equal to the existing instance features, take the vote as 1. If the new instance is not matching with the existing features, take the vote as 0. Okay, so delta v f of xi is the similarity between the new instance and the existing instance. If they are similar, take the count as 1. If they are not similar, take the count as 0. Add them up. From I equal to 1 to k, for all the k instances which are sensed to be similar with the new instance x cube, find out the similarities. If they are similar, increase the count by 1. If they are not similar, take it as 0. Okay, now add them up, find the odds. Now maximize those odds. Say this new instance, if let us think we have to classify it into positive or a negative class. Now this new instance gathered odds with respect to positive class, it gathered 6 odds, and with respect to negative class it gathered only 2 odds. So what is our objective now? Take the class which is having maximum odds. Means take the class from which more instances are matching with the new instance and assign the new instance to that class. Here, the new instance is matching with 6 instances which are from positive class, and the new instance is matching with only 2 instances which are from the negative class. So what is your objective? You have to assign it to a class which is having maximum odds, that is 6. So this new instance is being put into positive class, not the negative class. Okay, that is what we mean by this argmax. Argmax, the number of odds, calculate the number of odds wherever it is maximum, assigned to that particular class. That is the estimated value, that is the estimated target of xq, that is the estimated classification of xq, denoted by f cap of xq, new instance xq. Did you understand, students, clearly? Any doubt in this? Is it clear, Shashank?
Yes, ma'am.
Gaurish? Pooja?
Yes, ma'am.
Yes, ma'am.
Good. Now, as shown there, the value f of xq, that is the target, that is the class into which it is classified, returned by this algorithm as its estimate of f of xq is just the most common value of f. That is what we have taken, right? It is most common with positive class than with negative class. So we have assigned it to a positive class. It's just the most common value of f among k training examples nearest to q. So in this positive and negative class, among these k training examples, this xq is similar with 6 of the positive training examples and 2 of the negative training examples. So obviously we assign this to the positive class, that is f of xq. F is the function that is classification that is learned by the target function. Okay, now if we choose k equal to 1, now this is again important. If we choose k equal to 1 means if we choose that the number of neighbors is one nearest neighbor, just one nearest neighbor. Say you have a dot, circle, positive, positive, circle, like this. Okay, say you have two classes here, circle class and positive class, plus class. Now this is the new instance. Consider this as the new instance. This has to be classified either into circle class or plus class. In this case, if you take the similarity to be just equal to one nearest neighbor, then this is nearest to this plus, right? Immediately that will be assigned to the plus class because our criteria is to compare with only one neighbor with which it is nearest. Here it is nearest to positive class. So we automatically assign it to positive class. Now say you have to take 5 nearest neighbors or 4 nearest neighbors. Yeah, let us take 5 nearest neighbors. Now in this case, when you count the nearest neighbors, how many nearest neighbors are there in plus class? Only 2 of them. But in circle class, you have 1, 2, 3, 4, 5. 5 nearest neighbors. So when it is counted, its similarity with plus is only, it is having only 2 neighbors. But it is having circles, 5 nearest neighbors as circles. So automatically it will assign it to circle class. Did you understand what I'm trying to tell? If you take one nearest neighbor, in such case plus is very near to it. So it assigns to plus class. But if you take 5 nearest neighbors or 4 nearest neighbors, in that case, nearest neighbors plus is only, count is only 2. But 5 circles are nearest to the new data point. That is why it will be assigned to circle class rather than plus class if you take nearest neighbors to be 5. Okay, that is why we call it as local approximation. It is trying to make some approximations locally. It is not trying to consider all the data set instances at a time. That is why it is called as instance-based learning. Each and every instance it will consider locally to take a decision about the classification of this new instance. If the number of neighbors are less, plus is satisfying the criteria. So it is assigned to plus class. If the number of neighbors is more, in that case, circle is satisfying the criteria. So it will be assigned to circle class. That is how k nearest neighbor works. Now for larger values of k, the algorithm assigns the most common value among the k nearest training examples. That is what I said. It will take the most common value. In 5 nearest neighbors, circle is the most common value. So it will automatically assign to the circle class rather than plus class. See, that is what it is shown here. In this case, in this diagram, you observe this new data point plus. If you take nearest neighbor as 1, then to which instance it is near? To this plus instance. So it is automatically classified to a plus class. But if you take three nearest neighbors, then nearest plus it has only two instances, but nearest minuses it has three instances, and the criteria is three nearest neighbor. In that case, it will be assigned to negative class. Okay, this is how the nearest neighbor works. Now, the k nearest neighbor algorithm is easily adapted to approximating continuous value target functions also. Not only binary classification, not only multiple classification, but it can be changed in order to work with continuous value target functions also. But to accomplish this, in order to perform that task, we have the algorithm calculate the mean value of k nearest training examples rather than calculate their most common value. Only difference is in k nearest neighbor for discrete value target function, for binary classification or multiple classification, what we do, we calculate their most common value, right? Plus is the most common value which is near to the new data instance, or minus is the most common value to the nearest to the new data instance, that we will consider. But in discrete, in continuous value target function, what you do is you calculate the mean value of the k nearest training examples. You calculate the mean average of all the nearest training examples. Say the nearest training examples have some predicted value, right? 32, 34, 36. In that case, this new instance is matching with the training instances having this new instance dot is matching with the training instances having predicted values as 32, 34, 36. And it is also matching with another existing instance having value as 40. Now, this is more similar with the attributes of these three instances. So what is the outcome value here? 32, 34, 36. Find out the average, 34. Now that 34 will be assigned to this new data instance, that is dot. 40 is not assigned. Though it is near, it is having only one data instance that is similar with the attributes of the new instance. So it doesn't consider that. Here, three data points are having attributes that are similar with this new instance. So it will consider that set. And how is the target value assigned? Here we are not classifying. Classifying means you can simply put that new instance into this class. But we are not performing classification. You are calculating the continuous value. In that case, what you have to do is just sum up all the values which it is matching and find out the average of the labels, that is the predicted values, and that value will be the outcome label of outcome value of this particular new instance. So 34 can be assigned as the predicted value for this new instance. Got it? Now more precisely, to approximate a real value target function, f mapped from Rn to R. In previous case, in discrete value target function, what you did? The function is f is mapped from n-dimensional space to V, where V is the set of classes. Binary classification, 2 classes, multiple classification, more than 2 classes. But in this case, it is not mapping to different classes. It is mapping to a real value. That is 34 in this case, that is calculated. For that, we have changed the function a little. F is mapped from n-dimensional space Rn to real number space, to any numerical value. We replace the final line of the above algorithm by the line, that is k nearest neighbor algorithm we have already seen. That algorithm's last line we replace like this. Add up all the xi values which are similar to the new instance, find out the average, and that will be your new predicted value f cap of xq, new instance xq. F cap of xq is the estimated value or the predicted value of the new instance xq, which is The sum of all the target values, predicted target values, 32, 34, 36 in this case, add them up. That is why we have given sigma divided by k. How many values are there here? 3. So divided by 3. The average you find out is 34. So that will be the predicted value of the new instance xq. Did you understand now? Now, one obvious refinement to the k nearest neighbor algorithm is to weight the contribution of each of k neighbors according to their distance to the query point xq, giving greater weight to closer neighbors. So one refinement what we can do, one extra feature what we can add to this k nearest neighbor is, if you add some weight contribution, say some of the neighbors are very close to the new instance. In that case, add more weight to it. And some some instances are far away from the new instance. Add lesser weight to it. Okay, so that all the nearest neighbors will be given more weight, and all the far neighbors will be given lesser weight. Now, for example, in the algorithm of table, what we have seen in slide 7, which approximates discrete value target functions, we might weight the oath of each neighbor according to the inverse square of its distance from x cube. How this is done? Mathematically, it is represented like this. This can be accomplished by replacing the final line of the algorithm by, how do you replace the final line of the algorithm? By adding this weight factor. You're adding the weight factor here. How is this weight factor represented? It is the reciprocal of the distance between the new instance and the existing instance square. That is the Euclidean distance. The Euclidean distance between the new instance xq and the existing instance xi, reciprocal of that is taken as the weight. That weight is added to the final line of the algorithm. Now what happens here? Nearest neighbors will be given more weight and farther neighbors will be given less weight. Far neighbors means what? Listen carefully. Far neighbors means the distance is higher. When the distance is higher, reciprocal of the distance will be lower. So weight will be lower. Did you understand? And nearest neighbors will have distance lesser. Lesser distance means reciprocal of lesser distance means more weight. So nearest neighbors will be given more weight. So that will obviously increase the count of nearest neighbors weight. Okay, so the nearest neighbor's weight will be increased, and that can be approximated as the new instance's prediction. Got it, students? Now, to accommodate the case where the query point xq exactly matches one of the training instances xi and the denominator will become 0, we assign f cap of xq to be f of xi in this case. Okay, now they are dealing with some exceptional case also. Say there is a new instance and there is which is being compared with the existing instance which is also at the same place. In that case, there is no distance difference between them. Both are lying at the same point. In that case, this denominator will become 0. When this denominator becomes 0, weight will become infinite? No. In that case, f cap of xq can simply be f of xi. Means that will be automatically considered as the nearest neighbor without making the weight as infinite. Got it? If there are several such training examples, we assign the majority classification among them. This is obvious, right? If there are many training examples that are matching, then majority classification will be made according to majority vote. Now we can distance weight the instances for real value target functions in a similar fashion. If your target function is real valued, means some continuous numerical variable you want to predict, in the numerical value you want to predict. In that case, replacing the final line of the algorithm in this case can be like this. Final line of the k nearest neighbor, if you add weight, you have weight I multiplied by delta of the difference. But here what we are doing, because our target function is numerical value, you're going to predict numerical value, you're taking it as wi weight multiplied by f of xi, add them up, add all of the instances, existing instances along with their, multiply along with their weights, and add them up divided by the sum of weights. That will give you the estimated value. This is done for continuous valued target function. This is another way. Did you understand? The basic underlying algorithm k nearest neighbor is the same, but we are just modifying that so that it will match our classification problem as well as regression problem also. So you understood the beauty of it. Same algorithm we are having, but you are modifying it so that it will match your classification task or your regression task. Okay, so in order to match with the regression task, what you're doing, you just multiply the weights along with the instances, add them up, divide by the sum of the weights. That will be your predicted value. Now, if all training examples are considered when classifying a new query instance, we call the algorithm a global method, right? Say in this case, a new instance have to be classified. For this, if you consider all the values in order to classify this new instance, we call it as global method. But if only the nearest training examples are considered, say some nearest training examples are considered, not all, and we are taking it as, say one nearest neighbor is enough to categorize it, or two nearest neighbors are enough to categorize it, or three nearest neighbors are enough to categorize it. In that case, we call it as local method, because we are not considering all the training examples in the data set. We are just considering the nearest points. In that case, we call it as local method. But if you are trying to compare this new instance with all the data points in the data set, then we call it as global method, right? If students are competing only with the students in the same class, we call them as local competitors. But if they are competing with international students, then we call them as global competitors, right? In the same way, if all the instances are used for classification, it is called as global method. If only some of the instances are used, it is called as local method. In the next coming session, we'll discuss on locally weighted regression and radial basis functions. Now, what is KNN? Quickly answer the questions. Only two questions. What is KNN? Hereafter, I won't pronounce the entire form of this abbreviation. I'll just use KNN. So you should not wonder what it is. What is KNN? Pooja? What is KNN? Gaurish? K nearest neighbor. Didn't you notice that during the class? Today's entire discussion is on this algorithm, right? Why you're not ready to answer? K nearest neighbor algorithm. What is the distance measure used in K nearest neighbor? Mahalanobis distance or Euclidean distance?
Euclidean
Yeah, tell me.
distance.
Which distance measure?
Euclidean distance.
Yes, good. It is Euclidean distance measure, which is square root of x1 minus x2 whole square plus y1 minus y2 whole square. When x1, y1 are the attributes of point 1 and x2, y2 are the attributes of point 2. And when you are finding out the distance between P1 and P2, you can calculate it as square root of x1 minus x2 whole square plus y1 minus y2 whole square. Okay, students, can we proceed to the next topic, or you want me to repeat the same thing again? It is quite easy to understand, right? Today's concept. Just the simple introduction to instance-based learning with a basic algorithm, K nearest neighbor. Okay, then we'll meet in the next class.